We've seen in a previous video that when we have a mass bobbing up and down on a spring, as time goes on, it follows a pattern that looks like cosine, just like here, or sine. But we have some other parameters we can control. If I make the spring stiffer, what's going to happen to the mass? It's going to bob up and down faster, more oscillations per second. So that's changing this omega parameter. When it gets bigger, we get more oscillations per second. That could be a stiffer spring or a smaller mass. What if we vary when we start taking data? Well, that means we slide the function left or right, and that's this parameter p for the phase. Often we use the Greek letter phi when we're writing this in more formal mathematical notation. Let's take this back to 0. And we can have a slider there, sure. But what happens when we tie a note card to our mass on a spring? So I've got my mass hanging down here on a spring, and I attach a floppy note card to it. Now it looks like a cowboy hat. The air is going to be pushing against this. It'll be introducing drag, so it takes energy out of the system, and as it bobs up and down, the amplitude of these oscillations are going to get smaller. This happens in any realistic system because there's always some damping. So how do we include that? Well, last time we were in class, we saw that I can modify this, the amplitude. I know if I have a slider for amplitude, I can make the amplitude bigger. What happens if I make the amplitude negative? It just reverses the function from cosine to negative cosine. So we want an amplitude that is itself a function of our independent variable in this plot here, would be x, but we're actually talking about time. And we saw that the function we want to use is an exponential, and we need it to be an exponential of time. We also need it to decay. Let's call it b times t. What happens with that? Well, it helps if we use the same variable, bx. There we go. Now, when we make this parameter smaller, it takes longer for those oscillations to die away. When we make the parameter bigger, it takes less time. This is a damping parameter. Notice I get problems if my damping is negative. My amplitude blows up and I'm going to break my spring. So let's limit this slider. We're going to go from 0 to 3 steps at 0.01. So I can adjust this damping parameter to get more or fewer oscillations before the oscillations die away. Sometimes this is a thing you really want to do. Let's zoom in a little bit. I can actually tune my damping in some systems, like suppose I'm driving a Cadillac and I hit a bump. My car's going to bob up and down, but I don't want to be bobbing up and down 10 times every time I hit a bump. In a car like a Cadillac, we want to tune this so that we get just one oscillation, comes down, and gently back to equilibrium. Basically one period of oscillation. That's called critical damping. If we have, we really want to have that bump go away right away, we can overdamp the system so we don't get even one oscillation. We could make this really big and basically kill any overshoot and just come to 0. This is also, if you ever work in a kitchen, like a restaurant kitchen, we want to be able to adjust this so that, again, we get just one oscillation. You walk through the door, it swings back and comes to 0. So we're going to see how to model this in our code, and when we have collected actual data in Spider, let's get out of Desmos, into our Spider, we're reading this data like we saw last time. Take a look at the data, and we see that it's damping at some rate. What I'd really like to know is I can already measure the distance between these peaks and figure out what is the period of this, and therefore what's the frequency, measure it from peak to peak, peak to peak. But I'd like to also know how quickly do the peaks decay. So we're going to take a look at how to do that next.